Hello everyone, today we're going to look at the topic of voltage amplifiers and operational amplifiers as a type of voltage amplifiers. So let's get started. Amplifiers are two-port networks in which the output voltage or current is proportional to the input voltage or current. There are generally four types of amplifiers, namely voltage amplifier, in which the gain is defined as V out over VI, current amplifiers, in which the gain is equal to I out over II, transconductance amplifier are amplifiers in which the gain is I out over VI, and in transresistance amplifiers the gain is output voltage divided by input current. Our focus in this course is on voltage amplifiers. Now, voltage amplifiers can be accurately modeled with three circuit elements, namely Ri, input resistor, Rout, the output resistor, and a voltage dependent voltage source with the value of A0 multiplied by Vi. A good voltage amplifier has a large input resistance or Ri and a small output resistance or Rout. An ideal amplifier has Ri that goes to infinity and Rout that goes to 0. Operational amplifiers or op-amps are voltage amplifiers. As an example, this is the op-amp package for UA741 op-amp, and here is the circuitry inside this package. This op-amp consists of several transistors. We're going to study these BJT transistors in this course. So the IC consists of several transistors, resistors, and a diode and a capacitor. Op-amps are DC amplifiers, or in other words, they are direct coupled amplifiers, so you can directly connect the voltage sources to the input terminals of op-amp. They can amplify both AC signals and DC signals. They have very large gain, typically in the range of 10 to the power of 5 to 10 to the power of 6, and they have high input impedance, generally greater than 10 to 100 mega ohms, and they have low output resistance or less than 100 ohms. So the abstract model for op-amp is this triangular shape. It has two input terminals. This one is the negative terminal or the inverting terminal, and this one is the non-inverting terminal or the positive terminal. And here is where I get the output of my amplifier or op-amp. So to be able to turn on the op-amp, we need to connect it to external power supplies, plus Vs and negative Vs. And op-amps are constructed as a difference amplifier. The output signal in these op-amps is proportional to the difference between two input signals. In other words, Vout equals to A0 multiplied by Vd, which is A0 multiplied by Vp minus Vn. Linear model of op-amp consists of an input resistance that's connecting the two input terminals of op-amp, output resistance, and a voltage dependent voltage source. Because Ri is very large and Ro is very small, in the ideal model of op-amp we can assume that Ri goes to infinity and Rout goes to 0. That means there is an open circuit between two input terminals of op-amp. Which brings us to the first golden rule of op-amps that states in ideal op-amps, both IN and IP are almost equal to 0, so there is no current flowing into the input terminals of op-amp. So another important feature of op-amp is that op-amp will be in saturation without negative feedback because the gain is very high. So if you do not have any feedback, if you use op-amp just alone with by connecting two input signals to the input terminals of op-amp, it's not going to operate as a linear amplifier. And the reason is that let's consider an example. Say that the open loop gain is 10 to the power of 5 and Vsat is 15 volts. Vsaturation is the maximum output voltage that you can get from this op-amp. Vsaturation is going to be slightly less than positive Vs, and from the negative side slightly above a negative Vs value. So Vout is not going to exceed a V saturation value, and that's the maximum voltage that you can get at the output of this op-amp. Now with this Vsat of 15 volts and the gain, open loop gain of 10 to the power of 5, because I know that Vd equals to Vout over A0, I want to find the maximum Vd value. What is the largest signal difference of the input signals that I can amplify? And if you replace Vout with the maximum, with its maximum value, which is 15 volts, and this is 10 to the power of 5, you're going to end up with 150 microvolts. Say that this Vp is 0, or I'm connecting the positive terminal to the ground, and this is my input signal that's applied to the inverting terminal. That means the largest signal that I can amplify using this op-amp amplifier is 150 microvolt, which is a very small signal level. So this is one of the problems with using op-amp without any feedback. In addition, A0 is sensitive to the environmental and manufacturing situation, and a slight change on the open loop gain value is going to dramatically change the level of output voltage. To help with this problem, we can add a negative feedback to the original circuit. As you can see in this example, a portion of output voltage from this node is fed through the inverting terminal of op-amp through this R2 resistor. So R2 acts as a negative feedback resistor. Let's write the equations for Vout, Vi, and node voltage at the inverting terminal and see how this negative feedback works. So we're going to assume that this is an ideal op-amp, and with that, In is going to be equal to 0, Ip is going to be equal to 0, and from there I can write II using Ohm's law. I'm going to write II equals to Vi minus Vn divided by R1. Using KCL at this node, because there's no current going through the inverting terminal, II that flows through R1 is the same current that flows through R2. As a result, this is also equal to Vn minus Vout divided by R2. Let's rearrange this one. I'm going to have Vi over R1 plus Vout over R2 equals to 1 over R1 plus 1 over R2 multiplied by Vn, or that's equal to R1 R2 multiplied by R1 plus R2 divided by R1 R2 multiplied by Vn. From there, I can write Vn equals to R2 divided by R1 plus R2 multiplied by Vi plus R1 divided by R1 plus R2 multiplied by Vout. Okay, now if if Vi would increase, that's going to cause Vn to increase. But I have this relationship between the output and the difference between two input signals that are applied to the input terminals of this op-amp. Vout equals to A0 multiplied by Vd, which is A0 multiplied by Vp minus Vn. When Vn increases, this increase is going to cause a decrease in Vout. The negative feedback is going to stabilize the output voltage of op-amp circuit. This is the same circuit. We are going to solve the circuit and find the relationship between Vout and Vi. So this configuration is called inverting configuration because the input signal, or Vi, is connected to the op-amp through the inverting terminal. Okay, so let's write the same KCL equation for this Vn node, and this is my Vp, and use Ohm's law to find II, and then use it to find the relationship between Vout and Vi. So again, I'm going to assume ideal op-amps. I'm going to assume that this is an ideal op-amp. For that reason, IN is going to be equal to 0. IP is also going to be equal to 0. So II is going to be equal to VI minus VN divided by R1. It's going to be equal to VN minus Vout divided by R2. I want to eliminate Vn in this equation so that I would end up with an expression that relates Vout to Vi, and I can use this equation. I know that Vout is equal to A0 multiplied by Vd, which is A0 multiplied by Vp minus Vn. In this circuit, Vp is grounded, so with that it's equal to A0 multiplied by Vn. From there, Vn is equal to negative Vout divided by A0. Okay, so let's plug in this Vn value in the original equation here and find the relationship between Vout and Vi. So I'm going to write Vi over R1 plus Vout over R1 multiplied by A0 equals to so negative Vout divided by R2 times A0 minus Vout divided by R2. Let's rearrange the coefficients that are related to Vi in one side and bring the coefficients that are related to Vout to the other side. That's going to give me Vi over R1 equals to negative of 1 over R1 times A0 plus 1 over R2 times A0 plus 1 over R2 times Vout. With some further simplification, you're going to have Vout over Vi equals to negative R2 over Ri divided by 1 plus 1 over A0 multiplied by 1 plus R2 over R1. Okay, now because A0 is a very large number, if this quantity here, 1 plus R2 over R1, is much smaller than A0, then you can assume this value to be equal to 0 compared to 1, and then you can write the gain is equal to R2 over R1. Good. So as you can see here, the gain of this amplifier's op-amp circuit, or the ratio of Vout over Vi is a finite value that's equal to negative R2 over R1. So an important feature of op-amp circuit with negative feedback is that because Vout equals to A0 multiplied by Vd, obviously when the op-amp is not saturated and it operates as a linear amplifier, because Vout has a finite value and A0 is a very large number, that means this is finite, this is a very large number, that means this Vd must be a very small value, which means Vn and Vp are almost equal to each other. This brings us to the second golden rule of op-amp, which states for op-amp circuits with negative feedback, the op-amp adjusts its output voltage such that Vd is equal to 0, or the node voltages at the inverting and non-inverting terminals of op-amp are almost equal. Let's use the two golden rules of op-amps that we learned to solve the same op-amp inverting amplifier problem that we solved a few minutes ago, and see how we can use them to simplify the calculations of the gain. Again, we're going to assume that we are using an ideal op-amp. That means IN is almost equal to IP, that's equal to 0. So no current flows into the input terminals of op-amp. This is Vn and this is Vp. So I'm going to again write II equals to Vi minus Vn divided by R1, that is equal to Vn minus Vout divided by R2. Now, using the second golden rule of op-amps, because we have negative feedback that you can see through this resistor here, Vout is connected to the negative or inverting terminal of output, so we have negative feedback. And now, because of the presence of negative feedback, using the second golden rule of op-amps, Vn is almost equal to Vp, and because Vp is equal to 0, the positive terminal is connected to the ground, Vn is also going to be equal to 0, so I'm going to plug in 0 in here and here, and from the original equation I'm going to have VI over R1 equals to negative V out over R2. From there, V out over VI is going to be equal to negative R2 over R1, which is the same result that we had before using the longer way of calculating, finding the gain of this amplifier circuit. So the other thing to pay attention to is in this circuit is the gain, is that the gain has a negative sign. That means the input has a pi phase shift with respect to the output, or the output has a pi phase shift with respect to the input, and it's an inverting amplifier. Let's quickly take a look at the input and output resistance of this inverting amplifier configuration. Per definition, Ri is defined as Vi over Ii. This is the current that flows through R1. So and because I have negative feedback again in here, output is connected to the inverting terminal of input through this R2 resistor, and Vp is 0, so Vn is going to be equal to 0. From there, I can write Ii equals to Vi minus 0 divided by R1. From there, it's equal to Vi divided by R1. As a result, Ri is going to be equal to R1. So the input resistance of this amplifier circuit is equal to R1. The input resistance of op-amp itself is infinity. And in this circuit, the total circuit, the input resistance of the total circuit is equal to R1. How about R out? Because the output is taken from the two terminals of an ideal voltage source without any internal resistance, R out is equal to 0 in here for the op-amp itself. Because output is taken from two ends of the ideal voltage source, R out is going to be equal to 0 in this circuit. So in summary, we looked at operational amplifiers, the concept of negative feedback in op-amp circuits, and solved the voltage gain in the inverting op-amp circuit. Thank you for watching.